Okay, so let's go ahead and um, pick up where you left off. So we're working on chapter 11. And we are now looking at, so we're looking at depolarization, hyperpolarization, just to kind of refresh your memory. So we're looking at the different ways that you can depolarize and hyperpolarize the membrane, which is all important aspects of sort of the way the membranes work. So let's go ahead and take a look now at, so basically a voltage curve of our membrane. So basically we see this kind of very similar to what we saw with our muscle twitch graph, only in this case, we're not plotting tension over time, we're plotting voltage or potential over time. And so typically our resting membrane potential, which is what we have here at minus 70, let me go back to my original color. That's our starting point. And so then when we get to the place, like for instance, when we depolarize, so our membrane potential starts to move toward zero. Remember, it goes from like minus 70 and to minus 55. So it gets more positive in nature. You can see this little uptick in that voltage going from minus 70 to minus 60 to minus 55. That's your depolarization event. And then, of course, if it goes back down, then that's kind of a repolarization event back down to resting, which is basically what you have here in your flat line. Now then, to hyperpolarize, basically this is where you're getting further away from zero. If you remember, this is the situation where the membrane was moving from minus 70 to minus 90, right? So you're basically coming down further, and this is because of that hyperpolarization scenario where we have, like, for instance, the potassium leak kind of reinforcing that polarity. And that's kind of what we're talking about with hyperpolarization. Now, if you remember the depolarization, hyperpolarization, especially if like you get into like neurocommunication, like looking at analyzing the effects of different neurotransmitters like excitatory transmitters versus inhibitory transmitters. Remember, we said that excitatory neurotransmitters tend to depolarize the membrane. That excites the membrane to signal. And then typically inhibition is hyperpolarization. So you're hyperpolarizing it, making it kind of less sensitive to the signal itself. And so ultimately, this is kind of like what it looks like. So we're going to take our channel sort of image and we're going to connect it to our neuron. So here you can see you've got your cell body. In the first place, you're going to have the generation of your action potential. And so that's going to be caused by the sodium inrush. And so you can see how you have these successive sodium inrushes that basically depolarizes the membrane. And essentially it just starts to sort of gallop and propagate down the axon itself as you start to kind of move toward, in this particular case, the axon terminus. And then eventually, as it goes down the axon, kind of doing this sort of rolling sort of depolarization, eventually it's going to get down to wherever its target is. So you're going to get down to the axon terminus. And so, for instance, in our particular case, what we studied was the NMJ. So in this case, our target cell is going to be a skeletal muscle. And so as that action potential rolls down the axolemma, it's going to trigger those voltage-gated calcium channels, which will stimulate the release of the neurotransmitter in the synaptic cleft, where you will open up your ligand-gated sodium channels, and that will reignite the action potential in the sarcolemma. And of course, that is kind of where we left off last chapter, well, chapter 9, last chapter. When we were talking about the incoming action potential. Only now what we've done is we've sort of added a little bit to that incoming action potential by sort of taking a look at the sort of rolling propagation of action potential as it sort of rolls from the cell body all the way down the axon to the neuromuscular junction. So we kind of like extended that communication back a little bit. Now, the neurons themselves, when you take a look at these potentials and the changes in potentials, there's a couple of different types. So we talked a little bit already about resting membrane potential. We talked about depolarization. But the one thing we haven't really mentioned is this concept of a graded potential. And so graded potentials usually are small changes in the membrane potential, generally in a local area. And so the intensity of a graded potential can vary. So it can be quite small, it can actually be quite large, and it depends on the strength of the stimulus or the frequency of the stimulus. And so in addition to this, a graded potential doesn't have to be in one direction. We oftentimes will think of graded potentials as a depolarizing sort of a thing, but they can also be hyperpolarizing as well. So these graded potentials are just small fluctuations in the membrane potential. And ultimately, when we take a look at graded potentials, we generally are thinking of these as subthreshold in nature. However, the power of a graded potential is that you can sum up multiple graded potentials, or like an accumulation of a graded potential. They can add to each other. And then by adding to each other, they can sum up to and reach threshold, at which point you will get the floodgates to open. So just like we had before in chapter 9, remember when we had the kind of an all or nothing sort of a thing, where you had a threshold that you had to get up to? Same thing is also true here. So the threshold is the minimum. It's your bottom layer. It's your barrier. It's your point that you have to get to in order to open up all those sodium channels and get your action potential to ignite. Think of the concept of a threshold and a graded potential, sort of like when you're tipping over a domino, right? So basically, if I have a domino with something like this, there's my domino, right? If I start to push with my finger, with my fingernail, then as I slowly start to tip that domino, it starts to lean over. But there's a period there when it won't lean over enough to fall over. If I let it go, it'll basically kind of right itself. So the amount of force that I was putting on the domino was sub-threshold. You could think of it as sort of like a graded potential. I'm not pushing it hard enough to get to that magic point where the domino will fall and start falling on the other dominoes adjacent to it. Until I reach that point, the point at which it falls over, then it goes nowhere. And you can think of graded potential as the same thing. So as I slowly start to push on the domino, my force is slowly increasing. But then at some point, that domino is going to fall over, and then we're off to the races. Okay. So before I get to that point, though, that is kind of like sub-threshold force. So the domino is not falling over. I'm not pushing on it hard enough. That's like graded potential. And so I have to get to that minimum level in order to get these action potentials to go. So the graded potentials are also spread out, and it decreases in magnitude because it's spread out. And it's spread out over the surface of the plasma membrane, right? So the plasma membrane, being broad, high surface area, basically diffuses the gradient, that potential, and then sort of spreads out that force across that overall surface. And so that has a way of decreasing the magnitude, just like you have a dispersal force when you apply it across a broad area. Now, generally speaking, these graded potentials will come from a couple of places. First of all, you create a graded potential by binding to receptors, right? Ligand binding. And so we saw examples of that. That's like a ligand-gated sodium channel. Also, if you change the amount of charge across a membrane, either through leak channels or pumping or other sorts of means, that can create a graded potential. If you have mechanical stimulation or those physically distortable types of systems, those can create graded potentials as well. If you have temperature triggered types of situations, those can create graded potentials as well. And of course, you have spontaneous changes like random twitch and things of that nature. Notice one thing. All of these that we're mentioning here, these are all forms, and we talked about this in chapter 9, of channel gate control. Remember from our list, we talked about ligand-gated channels. We talked about charges or changes in charge across a membrane. That's voltage-gated channels. We talked about mechanically gated channels. And then in this chapter, we added to that a couple of others, right? We added temperature sensitive gates that open up from temperature, and touch receptors as well. That's another one, right? And then of course, added to this list is those spontaneous. So these basically, so when you're talking about allowing sodium to come through one of these gated systems, like we talked about in chapter 9 and also in this chapter, what you're creating initially are graded potentials. And those graded potentials have to sum up in order to meet threshold before you can get a full-on depolarization. Now, when you take a look at it, generally speaking, what's going to happen is this is all small volumes. So subthreshold volumes of sodium will enter the cell body. So this is basically level number 1. So basically what's going to happen is very small amounts of sodium will enter into the cell body. This will create a little bit of depolarization in the cell body. And then in 2 and 3, you'll have increased numbers of sodium coming in. So basically greater volumes coming in, which gives you greater degrees of depolarization. And that's the good thing about graded potentials, because graded potentials can be modulated. To represent anywhere from a slow trickle to a more robust flow of, in this case, sodium, or whatever ion it is that's doing this. And so that's basically just kind of coming in. And then, of course, in 4, you have a stimulus that can basically come into the cell body. That creates a little bit of a depolarization as well. And then when a second stimulus comes in, that's number 5. So you basically have 2 different stimuli coming in. Then, and basically, if it comes in at a time when the 4th one doesn't disappear yet, right? So it basically kind of overlaps with the 4th stimulus, then you can add the 2 together, and that can create an even larger depolarization. So here's kind of what it looks like graphically, right? So basically, when you have that first little trickle of sodium, you kind of get a little bit of a kind of a bump up, a very small depolarization uptick. And then in the second one, notice you kind of go from a depolarization and then you come right on back down. So you kind of get back down to resting membrane potential. And then the second one, you get a little bit more movement of sodium coming in. So you kind of get a little bit of a kind of a different, say, a larger curve with a bit more of a shoulder associated with its response to coming back down to resting membrane potential. And then in 3, notice you're getting a bigger depolarization curve. So what's happening is you're kind of like reinforcing the signal. So you're getting a little bit more robust with each new signal coming in. And then if 3 goes down, then you have the summation here, right? So you basically have 4 increasing its depolarization. But before 4 can go down, what happens is 5 comes in and just basically sort of re-ups it and basically kind of adds to where 4 is. And so what you get is this kind of giant curve. This is what's called summation, where you have two stimuli coming in right on top of each other that kind of reinforce each other's stimulus. Now you can imagine we're talking about events of the cell body here, right? Because ultimately this is essentially how we can communicate with nerves. Remember, we said that in the cell body, you're basically receiving all of these inputs and all these messages coming in. Some are excitatory, some are inhibitory. And this is an example of one way where you're basically able to input some sort of a message coming from, say, another neuron or something like that into the cell body. And so now these messages are here, these depolarization messages are here, and then the cell body is able to sort through all these messages. So let's take a look at some of the kind of characteristics. First of all, one of the characteristics we see is a stimulus. Open up some of these channels, sodium potassium chloride. And that's going to, because you're opening up new channels, that makes it more permeable to sodium, potassium, and chloride. Now, when you increase your permeability, especially to sodium, this is going to result into depolarization because the sodium is going to basically flow through its channel, right? And so if you have an increase in potassium or chloride, then that's going to result in hyperpolarization. Remember, we mentioned this before in the last class that the potassium's general urge is to move outside in response to its concentration gradient, which further reinforces the polarity of the membrane, thereby hyperpolarizing it. And that's basically what's going to happen if you increase your permeability. Remember, you increase your permeability by adding more leak channels, so you can get more potassium to flow through. Same thing's true for chloride, where it wants to come in against its concentration gradient or down its concentration gradient. So that makes it even more negative on the inside. And so increasing that permeability will also hyperpolarize it. So you're basically making it more, and the membrane more polar. Now, the graded potential itself, generally speaking, how strong it is, if it's a trickle or if it's a robust signal, is directly proportional to the strength of the stimulus. This is one of the ways that you can interpret the nature of the signal, is by basically adjusting your inrush, in this particular case of sodium, to be directly proportional to the gravity, if you will, of the strength of the stimulus itself. And so a very light stimulus will give you a very mild graded potential, which would have one particular consequence. A very strong stimulus would have a much stronger graded potential, giving you a different type of response. And so these graded potentials, even if they are gentle, if you back them up back on back, can also summate. And then when they summate, basically they can create a larger type of a response. So they can kind of sum up. And so this, what's this doing, if you're wondering why we care, which I'm sure several of you have come across that one. But the reason why we care about this is because when you take a look at graded potentials, what it does is, rather than just having sort of the crude sort of all or nothing, which is what you get with a threshold, what this gives you is a little bit more nuanced control and nuanced response in your system. So these graded potentials, like we mentioned before, are decremental in nature. That means they are spread over or diffused across large spaces, like, for instance, your plasma membrane. So they're very local. That's basically what that means. So you're thinking about local responses. So you're not using graded potentials, for instance, for your brain to communicate a contraction signal to your hamstrings, right? So The idea of summation is an important one, right? Because your depolarizing potentials can also summate across the way. Now let's go ahead and take a look at our action potentials and keep working on this. So when we take a look at neuronal communication, so we kind of talked a little bit about some of the nuts and bolts, sort of the mechanistic nitty gritty, if you will, of how some of these action potentials are set up and how these graded potentials work out. Now let's go ahead and apply this and sort of pull all this together and see if we can't figure out how exactly this sort of lays down the foundation for how these neurons are communicating with each other. So first of all, you all start with the graded potentials, right? So ultimately what will happen is the graded potentials will be what starts first, and they'll summate together, getting stronger and stronger at a region called the trigger zone. And then what will happen is they'll build up to reach threshold. And so once they reach threshold, then you open up the floodgates, and then it's just basically off to the races. And there's four main phases of your depolarization curve, or excuse me, of your action potential curve. The first one is depolarization, right? That's your inrush of sodium. We'll take a look at that here in just a little bit. And then after the depolarization event, you have to reset the system, right? So it's kind of like, you spring the mousetrap, that's like depolarization, and then you have to reset the mousetrap, and that's repolarization. And then once you repolarize it, then there's what's referred to as after potential, and then that's kind of like hyperpolarization. So you kind of overdo it a little bit, and then you kind of have to readjust it and bring it back to your normal resting membrane potential. But the important thing is, because it is threshold based, you're talking about here an all or none principle. So in this particular case, regardless of how strong the stimulus is, as long as it's greater than threshold, there is no modulation, right? So when it's an all or none principle, there's no modulation. So whether you are at threshold or whether you are way over threshold, doesn't matter. As long as you are over threshold or you meet threshold, then you've got an action potential. And so that's the reason why the graded potentials are useful, because since they're sub-threshold, they have a bit more of a nuanced kind of a modulation sort of an effect to them. Okay, so we take a look at the characteristics of graded potentials. Now we're going to take a look at the characteristics of the action potentials. So ultimately, this is going to happen when your graded potentials reach threshold. And at that point, it doesn't matter how much more over you go threshold. It is what it is. Threshold is threshold. And that basically gives you all of it or none of it. And that's your all or none kind of scenario. So once you reach threshold, it opens up the floodgates. And then if you don't reach threshold, those floodgates stay closed. So your depolarization event essentially is associated with sodium permeability. Matter of fact, it's associated with the movement of sodium into the cell. We saw this earlier in chapter 9. And of course, once you move that sodium into the cell, then you flip your voltage and you start triggering those voltage gated sodium channels. And that'll propagate even more depolarization. Now, repolarization is essentially a situation where you decrease the permeability of the membrane to sodium. Now, in this particular case, you don't understand. Now, what we talked about earlier, when you're talking about decreasing or increasing permeability and the leak channels, remember we were talking about increasing or decreasing permeability, say, for instance, to potassium or chloride or sodium by the number of leak channels you put into the membrane. The more leak channels you put in there, the more permeable you are to that particular ion. And so we were thinking about it as a function of the number of channels that you actually put in there, but that's not the way we're looking at permeability now. The way we're looking at permeability now is not necessarily by either adding or subtracting these sodium channels. Rather, what we are doing is we are gating them. We're closing these channels. That's how we change the permeability. As a matter of fact, that's how you change the permeability for the most part. Generally speaking, it's not really a functional strategy to basically add or take away entire channels as a way to increase or decrease your permeability. It's a little on the clumsy side, right? I mean, it's a lot of work to make a channel, and it's even more work to try to get that channel positioned correctly in the membrane so it can be functional. And then, of course, if you want to take them out to reduce your permeability, then that's even more of a task and a chore. And it just sounds like a lot of work for a whole lot of nothing. It's a lot easier and more efficient to basically increase and decrease your permeability, especially like within milliseconds, by simply just gating your channels and increasing and decreasing your permeability by either opening the gates or closing the gates. And that's basically how it actually works. So in this particular case, you're decreasing the permeability of sodium by closing the sodium gates. And in this case, you're increasing the permeability of potassium by opening the potassium gates. So there are gated potassium channels. And if you open those gated potassium channels, then you're increasing the number of channels that potassium can flow through, thereby increasing its permeability. This is in addition to the leak channels that already exist. And now, once you kind of get this swing of positive potassium swinging to the outside, what this does is it creates a charge balance, which has the effect of slowing down and then eventually stopping the movement of sodium into the cell. So in a lot of ways, it's kind of like the potassium is kind of used as sort of like a counterbalance or like a counterweight. As sodium rushes inward, basically the potassium rushes outward, and that kind of slows down the effect of sodium and keeps sodium from completely rushing to completion. So in this particular case, the sodium gates, that is to say the inactivation gates, will close, and the potassium voltage gates will open. And that allows you to kind of do this sort of counter movement. It's a lot like kind of on like one of those sailing yachts where you see them on the East Coast, all the rich people sailing their yachts and their little yacht races, and they're swinging the booms back and forth, and they're using their body as kind of like a counterweight to kind of handle and maintain the sail and the sail boom, using their body as a counterweight. That's kind of like the way potassium is. So as the sodium sort of swings wildly in one direction, potassium swings in the opposite direction and uses its sort of osmotic weight, so to speak, as a counterbalance to keep sodium from kind of flinging wildly out of control. And that's the important piece to the potassium. Now, then in addition to this, we have a couple of different periods that we also associate with this. Number one is what's called the two different refractory periods. So the first one is called the absolute refractory period. And at this particular point, there is no stimulus. It's not sensitive to any stimulus at all. Doesn't matter how strong it is. There's no sensitivity at all to stimulus during the absolute refractory period. As it starts to repolarize, it will start to reset a little bit. And as it kind of resets partially, it will enter into what's called a relative refractory period, where you do become sensitive to stimulus. But you have to have a stronger stimulus to do that, because you're still kind of repolarizing. You don't have you're not fully reset just yet. So it's kind of a little bit, takes a little bit of a stronger stimulus. So that's basically the sketch of your curve, right? So you have depolarization, repolarization. Within those, you have an absolute refractory period, a relative refractory period, and then that's an action potential. So then once you create your action potential, you have to propagate it, because you got to move it across distance, and that's basically what action potential propagation is. So you have to be able to roll this down the axon to the muscle fiber. And so ultimately, when you take a look at the strength will oftentimes determine the frequency of the action potentials. And of course, the more action potentials you have, the more signals you have, in this case, going out to the muscles. Here's what it looks like. So you start off, first of all, at resting membrane potential. And then initially, you start to get a little bit of that inrush, giving you a graded potential. It's sub-threshold, but it's climbing, 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 climbing. So for a little bit of time there's a sub-threshold increase in potential that is sub-threshold, and so that's a graded potential. Now then, once it hits threshold, then all of a sudden all the floodgates open up, all those sodium channels open up, and you get full-on unabashed depolarization. and it's very quick. We're talking about milliseconds here. And then right after that, hard on its heels, you get repolarization, where you basically get yourself back down to threshold. And then generally that repolarization works so well that you become hyperpolarized. That's your after potential. And then your sodium potassium pump will restore your original resting membrane potential. And then you're ready for another signal, another depolarization event. So let's go ahead and take a look at this. What we're going to do is we're going to break this down piece by piece, and we're going to walk you painstakingly and no doubt migraine inducing detail. So here's our resting membrane potential. So first of all, what we have in the beginning is the activation of the sodium gates. So the sodium gates are the red ones. Now, the important thing to remember is the sodium gates, unlike the potassium gates, have two gates on them. They have an internal and an external gate. Normally at rest, so this is your resting membrane potential. Normally, your voltage gates have one gate closed, and that gate is going to be the activation gate. So that is the one that is out there on the outside of the plasma membrane. So that gate is closed. The inside, the inactivation gate, is open. Either way, because you've got a two-gated system, that basically means that sodium is not flowing because it can never get through this first open or this first closed activation gate. That prevents the inflow of sodium. Now, the gated potassium channels, remember, these channels are different than the ones we talked about before. The ones we talked about before for potassium were leak channels. Those are maintained. Those are still in force here. They're still around here. Like if we were to take a look at a broader section of this membrane, we would see the potassium leak channels kind of allowing potassium to kind of go back and forth a little bit in response to its osmotic tensions. These are different. These are the voltage gated potassium channels, which are also gated, the purple ones, and they've got an outer membrane gating system, but they only have one gate. And this is basically where we start, at resting membrane potential. Now remember, the resting membrane potential at -70 is being maintained by a combination of the sodium potassium pump and the potassium leak channels and the sodium leak channels to a lesser degree, right? That's what's maintaining this -70 and keeping it the same. Then what's going to happen is we're going to hit a stimulus and we're going to hit a depolarization event. So now what happens is when we get a depolarization event or some sort of a stimulus, like a change in voltage, for instance, the activation gates on the sodium will open. That's these guys right here. So these external gates, which were closed before, will open, typically due to a voltage change. And when they open, you're going to have the inward movement of sodium, which is going to flood inside, making the membrane more positive on the inside. That is your depolarization. Now, this is going to cause more voltage gated sodium channels to open up because they're going to sense that voltage change, allowing even more sodium to diffuse in the cell. So the inrush initially of this first batch of sodium will cause a voltage change. It will be sensed by the adjacent voltage channel, which will open up and then allow sodium to rush in again. And this sodium will trigger the next voltage channel and so forth. And that's how you kind of get it propagating. And so you start to get these to kind of move back. And that happens until all of the voltage gated channels open up. And that's your depolarization event. So notice you get a very rapid, very quick inflow of sodium and a very rapid, quick increase in your voltage all the way up to, in this particular case, plus 35 millivolts. Okay, segment number 3. Now that we've depolarized, what about repolarization? Because as soon as we depolarize, then it's time to reset your system and you get right to work. You don't linger. So what happens during repolarization, so it's reached its maximum depolarization. What happens here is the inactivation gates. That's the inner gates. These guys will close. So that's these guys here on the inside. Those inactivation gates on sodium channels will close. That stops the inflow of sodium, but at the same time, your potassium channels will open. And so because your potassium channels are opening, that's going to allow potassium to rush outward, which kind of stops the inflow of sodium, both of those together. And potassium movement out of the cell increases, causing a repolarization. Why? Because you are adding new positive charge to the outside. In the form, in this case, of potassium. So because remember, the sodium flooded inward, so the sodium is no longer able to maintain positivity outside the cell. So when you open up the potassium gates, the potassium rushes out, and that reestablishes a positivishness on the outside. There's that word again. And so that basically kind of reestablishes, if you will, repolarizes that. And then that's basically a repolarization event. Now, at the end of repolarization, in this hyperpolarization phase, the activation gates of sodium will close. That's these outer gates will close, and the inactivation gates will open. So they kind of reset themselves. Back to their original form. But if you notice, your potassium gates are still open, still allowing potassium to flow through, further reestablishing the polarity of the membrane and recreating the hyperpolarization. Now, the after potential, now this is kind of the beginnings of it, right? So basically you go below threshold and you go a little beyond resting membrane potential because of the increase in potassium that's coming out. So this keeps piling up out there, hyperpolarizing it. And then the after potential, or the point of hyperpolarization is caused because these potassium channels are still open. And they're open for a little bit longer than it usually takes to get to your membrane potential. So you're kind of purposely overshooting it. You're kind of giving it a little extra long time to make sure you get down to resting membrane potential. And then ultimately what's going to happen is you're going to establish this kind of hyperpolarized segment. Now then, the last piece of it, once you've hyperpolarized, is you readjust back down to resting membrane potential. And you use your good friend sodium potassium pump to readjust the hyperpolarized membrane back to resting membrane potential. So by taking the potassiums that have piled up outside, those potassiums out here, and moving them back into the cell, and taking all those sodiums that have piled up on the inside, and then moving those back to the outside, reestablishing and recreating that gradient that we had at the very beginning. So at this particular point as well, before you actually start this readjustment, the one thing you need to understand is that what triggers this is the voltage gated potassium channels have to close. So now you've got the closure of your potassium channels. Your sodium will readjust back to resting membrane potential, and then it'll be maintained by the leak channels. basically bringing us all the way back to the very beginning. A resting membrane potential with a sodium concentration high on the outside, potassium high on the inside, maintained at -70 by the osmotic leakage of potassium mostly, but also sodium and maybe a little bit of chloride. And then guess what you do? You do it all over again. Then you get another stimulus, which then goes through the entire process all over again. And you do this for as many times as you send an action potential. So these last slides right here, these are really, really good slides. So from about probably slide 50 all the way to 56. If you can work your way through those slides kind of the way we just did, and you can kind of rattle that off and sort of feel really confident about how everything is working in there, you have a really good handle on neurophysiology, not just for this chapter, but you also have a really good handle on the physiology that also underlies the entire muscle physiology piece, because the muscle physiology part is actually built on the neurophysiology part, right? Like with the neuromuscular junction. So if you're able to sort of understand those slides, those 6 slides really, really well, then you've got a really good foundation to build on. Okay, let's go ahead and take a look at refractory periods. So when you take a look at your depolarization curve, underneath the depolarization repolarization curve is this purple zone. This is your absolute refractory period. You have complete insensitivity. You're not listening anymore because it's like the mousetrap has been sprung, right? So a mousetrap that has been sprung is not a danger to a mouse, right? Because it doesn't have any energy in it anymore. It's already been released. It's already been sprung. And so it's insensitive. And so this is going to be going from the beginning of your action potential when you start to depolarize till pretty close to the end of your repolarization, just before the hyperpolarization. And it doesn't matter what kind of stimulus you send or how strong it is, or if you send a lot. If it's in the absolute refractory period, you're not going to get a response. You have to wait until you reset the system so that you can make another response to your incoming stimulation. Now, the pink zone is the relative refractory period. So this is basically where you have a little bit of reset. You're not perfect yet because you haven't gotten yourself adjusted back to resting membrane potential, but you do have a little bit of reset here. So you are partially sensitive to stimulus. But generally speaking, you have to get a little bit of a stronger stimulus. So it has to be a little stronger than threshold to get you there. Why? Because you're still hyperpolarized. So this has to be stronger because you're still hyperpolarized. So for instance, instead of going from here to here, which would be a normal stimulus, now you have to go from here to here, which requires a stronger stimulus to get up to threshold. But it is possible. So now that we've generated an action potential, let's go ahead and take a look at some potential strategies for propagation. So first of all, the important thing to understand is that the graded potential sums up to an action potential at the trigger zone, and that's going to cause the action potential. Now, generally speaking, we have 2 different forms of conduction. One, which is called continuous conduction, right? This is basically where the action potential will stimulate the adjacent membrane. And so ultimately, this will create an action potential right next to it in the next location, like in the membrane right next to you. You generally can't go backwards because you're already depolarized. The membrane that you just came from is still depolarized. So there's only one way to go, and that's forward. So this is basically the way we've been looking at it. So like, for instance, when you have a graded potential that creates a depolarization, and then that kind of tips over the adjacent domino, which tips over the adjacent domino, which tips over the adjacent domino. That basically is like continuous conduction. It's just rolling from one little section of membrane to the next, to the next. Now, there is another type of propagation that you oftentimes see, especially in the peripheral nervous system. That's called saltatory conduction. So this basically is conduction by leaps and bounds, instead of just like crawling from one segment of the membrane to the next. So this is kind of what it looks like. So action potential propagation in typically an unmyelinated axon tends to be continuous. Here you can see a region. This is going to be a region of the neuron that basically is going to be depolarized. So you can see the orange area. That's going to be the newly depolarized membrane. And so you can see the depolarization is happening in a local area. So this is what's called a local current. That's what happens. So that inrush of sodium creates what's called a local current. That's the movement of the sodium. And that local current will then kind of move to the adjacent membrane. And by doing so, it'll change the characteristics of that voltage gate, and then it'll open up. So here, for instance, you can see you get a depolarization, a local current influx of sodiums inward, causing it to be positive on the inside. And what happens is this local current will basically drift over, diffuses toward the next piece of membrane next to it. And then that's going to cause those channels to open up. And then you'll have a new inrush of sodium coming in. So that's the new depolarized piece. Now, upstream, the segment that's just upstream is now in its refractory period, right? So it's no longer sensitive because now you're in the reset mode. You're in repolarization mode just upstream. So basically, when the sodium diffuses, it goes to the next adjacent membrane where it will depolarize that petite piece of membrane. And now the next piece is going to go into repolarization mode. And then so forth. So basically it ends up just kind of going in this direction. And so this is going to basically roll into this next segment, which is going to then roll into the next segment, which is going to roll in the next segment, and so forth. And so that's basically what's called continuous propagation. Typically, the important thing to understand is it works with unmyelinated axons. It works because communication is between closely associated neurons. That is to say, the cell that you're talking to is just right next to you. So you don't have to like really send this message to far reaches of the body. The one you're talking to is right next to you, right? So in this particular case, you can like talk to them in a whisper. Okay. Now, saltatory conduction, this basically is propagation across long distances. This is what's happening when your brain is sending a contraction signal, and it's sending it down a motor neuron that has to go out to the periphery of your body. Okay, so it has to go a long ways. And the idea is you want to get it out there quickly because you want to be able to send this information. So you have the same basic idea, right? So your action potential, which is our orange, has been created in the axon. So you can see here, this is your little point of depolarization. So right here. And typically that depolarization, because your peripheral nervous system right? So basically this is your Schwann cell. So this is a peripheral nervous system nerve. So because your neuron is wrapped up in these Schwann cells and you got these little nodes of Ranvier, these little unsheathed areas of no myelin, the depolarization occurs at this node. Now, essentially, once this local current comes in, because it can't talk to the adjacent membrane because this node is in the way, right? This sheath is in the way, insulating the axon, so it can't get to the adjacent membrane. So it tries over here, nope, can't get there, can't get there, can't get there. So it's all basically insulated and wrapped up. So the flow or this local current will flow all the way through the axon before it can get to another region where it can depolarize, and that would be the next node. So now you can see in the second step, it's flown all the way through the axon to the next node where it depolarizes the new node. Now the previous node is now repolarizing. It's resetting itself. In this case now, what's going to happen is that inflow, that local current of sodium is going to flow through the axon again until it gets to the third node, in which case it's going to depolarize the third node while the second one is repolarizing and the first one's already ready for the next stimulus because it's already fully reset. And the same thing happens here. So the third one will flow through until it gets to the fourth node and so on and so forth. So what's happening is instead of flowing from one segment of membrane to the next, to the next, to the next, like continuous propagation, what's happening is you're jumping from node to node to node. So essentially you're moving faster down the axon. And that allows you to get quick communication and quick propagation. Now, you may ask, well, wait a minute. If it's flowing down this little area where the Schwann cells are covering it up, then how come it's not depolarizing the membrane that's being covered up by the Schwann cells? And it's very simple. Because there's no voltage-gated sodium channels there. So the voltage-gated sodium channels are going to be clustered in the nodes of Ranvier. So there literally is no channel for this local current of sodium to open up. You don't get to your next channel until you get to your node. And that forces the sodium to have to move all the way through that little conduit, that little segment that's sheathed with the myelin in order to get to the next node before it can depolarize it. So those are two strategies of propagation. You have propagation that's continuous for close communication between two neurons that are close together. Oftentimes you use unmyelinated communication like that when you have two neurons or multiple neurons that are coordinating activities, and they're basically all about coordination and things of that nature. Generally speaking, you see myelinated situations when you're trying to send a signal across distance and you need to get there as fast as you can. So the synapse is something we've covered a little bit already because we talked a lot about it in chapter 9. And so this is your junction between the two cells, right? So basically where the action potential in one cell is going to cause an action potential in another. And there's different types of synapses or different types of cells in the synapse, right? So first of all, we have what's called the presynaptic cell. So this is the cell that's transmitting that signal or that action potential. And then we have the postsynaptic, which is the target cell, the receiving signal. Now, if you were listening carefully in chapter 9, you noticed that this was the set of terminologies I tended to use when talking about the neuromuscular junction, is presynaptic and postsynaptic, because it is essentially a neural connection between those two. Now, generally speaking, we have two overall types of synapses. We have what's called an electrical synapse, and we have a chemical synapse. So in the electrical synapses, this is basically, generally we see these when we are involving things like gap junctions. And so in gap junctions, what happens is you allow a graded flow of ion to move between adjacent cells. So two cells that are connected together, And you have what's called connexons, which are like little tubes that connect the cell membrane. So this is what it looks like. So cardiac muscle, for instance, has a lot of these gap junctions. So if you have two different cells like this, so you have the connexons, which are like little protein tubes that connect these guys together. So here's cell number 1, and here's cell number 2. So these are the gap junctions. So if you have an ion that rushes through this, then you can have this sort of depolarization event, like a synapse, right? So this happens and oftentimes when your two cells have to have coordinated activity. They have to basically operate and act at the same time. So they have to coordinate their responses. Like the cardiac muscle cell has to all contract at the same time. Smooth muscles can also be connected by gap junctions. This is necessary anytime you have to have a good communication and good unison or unified response. And so that's where you see it. So those are electrical synapses, typically very specifically located in these particular areas. And so, for instance, this is kind of what it looks like, a little bit more of a fancified version other than my little sketches. So your action potential will come into one cell. So you can see basically it kind of comes into one cell here, and it's going to produce a little bit of a local current. And so what happens then is from the one cell, it'll flow through the gap junction to the other cell. And so that flow through of sodium creates an action potential in the adjacent cell. So you can see how your local current will basically trigger an action potential in the first cell, but part of that will flow through the gap junction and then stimulate also an action potential in the second cell. This basically allows both cells, 1 and 2, to essentially experience and generate an action potential at pretty much the same time. And that is the way you synchronize those two cells together and any other cells that are connected with gap junctions. And so typically, like I said, those are mostly, for the most part, I mean, in AMP, you'll probably run into those if you're talking about cardiac muscle, and that's where you're going to largely see those. Okay, now let's take a look at chemical synapses. Now, chemical synapses are kind of the ones that we usually think of, right? So essentially, when you take a look at a chemical synapse, you've got a couple of different structures. So this will sound very reminiscent because we covered this in chapter 9, right? But basically, you have a couple of main components. First of all, the first thing you're going to have is a presynaptic terminal. So this is the end of that presynaptic cell axon. So the axon terminus basically is going to be one component, and then that's going to be followed by your synaptic cleft. That's that little space between your presynaptic and postsynaptic membranes. And then you're going to have your postsynaptic membrane, which is essentially the membrane of the target cell. In this case, we have to expand our definition of target cell because in chapter 9, since we're talking about muscle physiology, our target cell was a skeletal muscle. But in this particular case, because now we're talking about neurons, it can be a muscle cell, that's true, but your target cell can also be a gland or it can be another neuron. So we have to expand our definition of who the postsynaptic target now is. And so the way that you communicate through this particular system is by using a chemical molecule, for instance, our neurotransmitters, which are typically released by action potentials, like we saw before in chapter 9, from the presynaptic terminal by way of releasing these synaptic vesicles that open or that basically fuse, go through exocytosis in response to the opening of calcium from these voltage gated calcium channels that allow the calcium to rush in to the axonal terminus, causing the synaptic vesicles to fuse, and then they dump their neurotransmitter in the synaptic cleft. And of course, the neurotransmitter will diffuse across the synapse where they will find a ligand, typically a ligand gated ion channel with a receptor for that neurotransmitter waiting on the other side. So this should all look very much like review for chapter 9. So this is kind of what it looks like. That's really, really tiny, but that's like the whole thing. And so this looks almost like exactly what we saw in chapter 9 because, well, it kind of is, right? So basically you've got your action potential coming through. It's going to trigger your voltage gated calcium channels, which will allow calcium to rush in, and that is going to signal these synaptic vesicles to fuse with the axonal terminus, the membrane of the axonal terminus, releasing the neurotransmitter, which will then bind to ligand-gated sodium channels on the postsynaptic membrane, allowing the inrush of sodium and the recreation of the action potential in the target membrane protein. So this is what it looks like up close. You can see your ligand gates will open and your sodium will inrush, creating a depolarization event, and that will basically reignite the action potential in the target cell. So then, of course, just like we mentioned before in chapter 9, you can notice there's a lot of overlap between 9 and 11 in this particular section. So just consider this review and extension, right? Your neurotransmitters have to be removed. And so this is different for each neurotransmitter in each synapse, right? So basically, neurotransmitters are designed to create short-term effects, not long-term effects. If you want long-term effects, you typically use the endocrine system. If you want short-term effects, you typically use the nervous system, right? So these neurotransmitters typically are rapidly destroyed and removed from the cleft so you can reset the system. So what this basically does is it resets the system so that you can have another signal coming through. And so this is kind of what it looks like as it comes through. So this is basically the removal. So essentially, in this particular case, this is a neuromuscular junction that we're looking at. More than likely. So what's happened is you released your acetylcholine into the cleft. It's bound to the ligand-gated sodium channels, and now the idea is that you have to release. So you have to release these acetylcholine molecules from the ligand gates, so they have to let them go. And the second piece, then, you're going to have the breakdown of the acetylcholine by acetylcholinesterase, and it's going to cut it into its two components. So here you can see you've got choline, which is the yellow component. That gets taken up by an active transporter in your presynaptic membrane that takes up choline along with the sodium. It recycles the choline and adds it to an acetyl-CoA, which you can get from respiration, where that's the starting molecule for Krebs cycle in cellular respiration. And so you can take that acetate group from acetyl-CoA, attach it to your choline, and reestablish and recreate acetylcholine, where you'll package it into your vesicles, awaiting the next action potential. The acetate, or the acetic acid, can then go off and actually can be converted into acetyl-CoA. And it can be fed into metabolism, your cellular respiration. So don't just lose it, just use it, right? And so by doing that, you basically have a mechanism to not only release your neurotransmitter into the cleft, but also to clean all that out and to reset the system so that you have a fresh synapse or synaptic cleft to basically to start over again. Now that's acetylcholine, but what about other neurotransmitters? How do they work, right? So how do you remove, for instance, norepinephrine, which is one of the adrenalins? Well, the first thing is the same basic idea, right? The first step is you have to release the norepinephrine into the cleft itself. And then the norepinephrine, typically, rather than being broken down, is actually taken up by an active transporter. So it's going to be moved into the presynaptic terminal. And then from here, it's got two destinations. So it can be repackaged into the vesicles. You can take your norepinephrine, repackage that into your vesicles, ready for re-release. Or you can use another enzyme called monoamine oxidase, which can actually break down norepinephrine and basically return it into inactive metabolites and oftentimes waste molecules that you can get rid of. So you can either reuse it or you can break it down and basically turn it into metabolites. So let's take a look. So those are neurotransmitters in the chemical situation. But now let's go ahead and take a look at some of the receptors, right? So the important thing to remember about the receptors is the receptors are specific, right? So basically, your neurotransmitter will fit only in one receptor. So these guys are specific for their neurotransmitter. And so if you don't have a receptor, your neurotransmitter will have no effect on you. So neurotransmitters can either be excitatory, they can excite a cell, or they can be inhibitory. They can inhibit a cell. So like for instance, like a norepinephrine type of neurotransmitter can sort of like regulate itself. So some neurotransmitters can do this. Acetylcholine can't do this, but norepinephrine can actually feed back, and it can bind to presynaptic terminal and modulate its own release. So it can actually regulate its own release. So like if you're getting too much, then it can regulate that. So this is kind of what it looks like. So here basically you can see a neuron to neuron junction where you have a neurotransmitter that will open up a ligand gate that allows a graded potential to come into the cell body. This creates a depolarization event as the sodium rushes in stage 2. That creates your depolarization. And then, of course, you get your repolarization with your open potassium channels to reset the system. And then as that starts to depolarize the adjacent membrane, it basically just starts to roll slowly from one to another, to another, to another, until you get propagation of your action potential all the way down your axon, until eventually you hit your synapse, where you have the opening of the voltage-gated sodium channel or the voltage-gated calcium channels, which then causes the release of neurotransmitter to the cleft by fusing the synaptic vesicles. Those neurotransmitters will bind to ligand gates, which will allow the inrush of sodium, which will redepolarize the membrane of the target cell, reigniting the action potential in the target cell membrane. So this is kind of like the full from the beginning to the end. This is the entire story. So just to basically take a look at a quick sum in the last few minutes that we have, we start first of all with our graded potential, which is a stimulation that essentially initiates this graded potential, which can then open up the sodium channels, and it can be summated until it reaches threshold. That's the key piece to graded potentials, is they haven't reached threshold first. Once they do reach threshold, then we move into number 2, which is depolarization. This is happening at the axon hillock. The axon hillock is this little area right in here. So this little area right there is the axon hillock. That's kind of where the trigger zone is that we've been talking about. That's where your axon hillock is. And so this basically will reach threshold. And so once you reach threshold, then all of your voltage gates will open up, and then you'll get an influx of sodium, and this results in rapid depolarization, followed hard on its heels by rapid repolarization, where the sodium channels will close, become inactivated. The potassium channels will open up, allowing potassium to move outward, repolarizing the membrane. And then once it repolarizes, while that piece is repolarizing, then we are propagating the action potential as it moves from one segment of membrane to the next. Basically, it's starting at the axon hillock. Those local currents will basically move to the next area. That's the adjacent membrane, where it will reach threshold, and then it basically leads to the propagation, continuous or saltatory, depending on your structure, as the action potentials start to move down the axon heading toward the presynaptic terminal. Now, the synaptic communication, basically, you have your action potential reaching the presynaptic terminal where it's going to release the neurotransmitters to the postsynaptic cell. So that's basically a summary. Hopefully that'll be useful for you guys, that kind of stepwise summary. Now, the neurotransmitters and the neuromodulators basically are the chemical messengers. So we talked a little bit about the nature of the receptors. Now we want to take a little closer look at some of the neurotransmitters, right? So basically you have neurotransmitters and neuromodulators. These are all chemical messengers that are secreted by neurons, and you can create different types. So there's a lot of neurotransmitters and neuromodulators, potentially about 100-ish or so. So to be a neurotransmitter, you basically have to have a couple of criteria. Number one, you have to be made by a neuron and stored in these synaptic vesicles. That's one piece. The next one is an action potential has to stimulate your release, right? Just like we saw in the synaptic clefts. The third criteria is basically you have to bind to a receptor on your postsynaptic membrane, just like acetylcholine. And the fourth criteria is you must provoke a response, typically a reignition of depolarization in the postsynaptic cell. Now then, when you classify your neurotransmitters, you can classify them on a couple of ways. So first of all, you can classify them by the chemical structure. That's one way. You can classify them by their effects on postsynaptic membranes. That's another way, like excitatory, inhibitory. By the mechanism of how they act. That's another way. But generally speaking, when you take a look at neurotransmitters, they typically are excitatory or inhibitory. And so when you take a look at this, they have a couple of effects, right? So you have ionotropic effect, which is essentially where you bind to ion channels. That's kind of like acetylcholine, like we saw there. Or you have metabotropic effect, which is essentially a G protein linked receptor. So this basically results in what's called cell signaling. So you kind of signal a cell to do something. And so what the actual neurotransmitter does is determined not by the neurotransmitter, but by the cell and what it designs its receptor to do. So these are some of the major classes of neurotransmitters. So we have acetylcholine, we've been talking about a lot. And so this is the most common one. We also have a type of neurotransmitter called biogenic amines. These are what's called catecholamines and indoleamines. So for instance, serotonin and dopamine, norepinephrine, these are the biogenic amines. Some amino acids are neurotransmitters. For instance, GABA, glycine, and glutamate are all types of neurotransmitters. Some nucleotides are. So purines, for instance, nitrogen-containing compounds for nucleic acids, for instance, adenosine and ATP can be types of neurotransmitters. They can also be proteins, so neuropeptides, for instance, short-chain amino acids. For instance, we have substance P made in the intestines, and endorphins are types of neuropeptides. Endorphins are sort of like your natural morphine. So basically, in heavy physical trauma, endorphins flood your system to kind of take you offline, to kind of help sort of mute the pain and the trauma of physical trauma. Also, some gases and lipids can also be amino acids. So for instance, nitric oxide, which is NO, is a type of neurotransmitter. Carbon monoxide can be a neurotransmitter. Endocannabinoids typically can also be, those are lipids, can also be types of neurotransmitters. So there's a lot of different types of neurotransmitters. And for you table types, this is your table, right? So you have your different types, your biogenic amines, your acetylcholines, your amino acids, your purines, your neuropeptides, your gases and lipids. So basically this is just the table version of what we just had in this particular slide. And guess what? That brings us to the end of chapter 11.